So now let's move on to some real situations, or not, well, some fake real situations, of course, as usual. Except this time, I'm going to be doing something that's more commonly going to happen in the real world. I'm comparing two different groups. I don't know the true mean of either group or the true standard deviation of either group, but I want to still calculate what the probability is that the two means are equal to one another for the two groups. I'm interested in comparing the means of the two populations. We're going to use X bar, the means of the samples, to get to that point, but it's really the two populations I'm really interested in, their means. So I'm going to take a look at this first one. I'm going to open up Excel. And I'm going to go on to do, I have a file in here that's also has open. Okay, let's see, desktop, data. Okay, let me see which one we're looking for. Here we go. Okay, this one. Okay, here's my two groups. Okay, let's say, well, first of all, first thing I'm going to do is I'm going to start formalizing this a little bit. First of all, what am I trying to prove here? I'm trying to prove the mean for males is different than the mean for females, right? And when I want to prove that they're different, in order to start off, what do I start off? What's my assumption when I start off before I go ahead and prove that they're different? I start from ground zero. I start from the assumption that they're the same. And then I force myself to prove that they're different. Okay, so what do we call that assumption that they're the same? Okay, H null. Okay, null hypothesis, right? Okay, so how would I state that? Well, you could, yeah, there's a couple of ways. We could say that the difference of the two means is that the difference is equal to zero. I'm going to do it a little bit more informally. I'm going to say the mean for the males is equal to the mean for the females. Okay, how's that? And what's my alternative hypothesis? That they're different. Now, this gets a little complicated. I could say to myself, well, maybe I know that one can't be less than the other can't be, maybe I know whether we're dealing with heights, and I'm going to start with the assumption, well, I don't think female heights are greater than male heights, but we're going to start, at least for today, only working with situations where the alternative hypothesis is that there's a difference. We're not going to speculate about whether the difference is one group A is greater than group B, or group B is greater than group A. We're just going to start with the assumption that they're different, or that the alternative is that they're different. Okay, so what's our alternative? The mean for the males is equal to the mean for is not equal to the mean for the females. Okay, null hypothesis, alternative hypothesis now chosen. Okay, so how am I going to prove that? I'm going to prove that by comparing the two means to see if the means are far enough apart that I can say with 95% certainty, or less than 5% chance of being wrong, that they're really different, that it's not true that they're the same. Okay, so how am I going to do this? How do I calculate the t-value now? I don't have a x bar and a mean. I have two x bars, don't I? Right, I have x bar for females. Let's see, minus x bar for males, right? And I'm going to take the difference between the two means, the two sample means, and divide it by the standard error. Okay, so the beginning of this should be pretty simple, right? Yes. Yeah, I did it twice, didn't I? Yeah, I wrote that in there twice. Yeah. Okay. X bar males, X bar. Did I get it right that time? I got it right that time, right? Okay. So let's see how different they really are. So X bar for males and X bar for females. Right, but this is going to be equal to average. Okay, you guys can do this while we're working on it, right? And I'm going to take the males And then I'm going to take the females equals average. Okay, and there's the difference between them. So I got the top part of that equation, don't I? So now I need to calculate the standard error. Okay. Okay, well, I'm going to go over here to the corner, so where I have a little bit of spare space. I'm going to calculate standard deviation for females and standard deviation for males, just to get a look at them. Okay, so what is it going to be equal to females? I'm going to start with, I'm going to do males on top. I'll try and keep them in the same order from now on. A little less confusing. Oops. Okay, standard deviation for males is equal to standard deviation of the sample, which is an approximation of the standard deviation for the population males. Okay, let's get these, and this is the females. Okay, 1.96. Okay, well, gee, I got a little bit of a problem here, don't I? The equation I want to use is x bar for females minus x bar for males over the standard error. I only want one standard error, right? So now, which of those two standard errors should I use? Or maybe I should combine them in some form or another. Okay, I put on Blackboard a document, which is I hope will kind of wind up helping you in the long run. Okay, different variations of the t-test. Okay, in this first variation I have, at least of the two sample t-tests, this first variation I have that the standard deviations of the two groups are equal. And the second one I have is the standard deviations of the two samples or populations are not equal. So what do you think in our case? Are they equal or are they unequal? Well, you know, they're always going to be different. The question is, are they different enough for you to say that they're not equal, right? Does that sound like a familiar problem to you? Are they equal or not equal, right? It's the same deal here. Our null hypothesis kind of is that they're the same, and maybe we have to prove that they're different. For our purposes in calculating this by hand, if one is not double the other, we're going to assume that they're the same. Okay? If they're one is more than double and one is less than half of the other, then we'll call them different. Okay, so in this case, we're going to call them the same. So how do I handle standard deviations that are the same? Right? Well, let's go back here. Let's see. That was our first variation. Okay, so let's see what I have to do. See, t is equal to the difference between the two means over the square root. Whoop, I got the wrong one. Okay. First thing I'm going to do is I'm going to pool the two standard deviations. What am I doing there? I'm saying to myself, if the two standard deviations of these populations are the same, I can gain an advantage by just combining the 18 numbers. Instead of using 9 numbers to calculate standard deviation, I'm going to combine them, pool them together. So I'm basically using all 18 numbers to get a better estimate of the variability. Okay, so when we're going to assume that they're equal, we're going to calculate a pooled standard deviation. So I'm going to try and keep that out there while we calculate this. Okay, so what is that pooled standard deviation equal to? Pooled standard deviation is going to be equal to the square root of, I'm actually going to do this in a couple of steps just to make it easier. The sample size of group 1 minus 1, so that's going to be 8. It's going to be 8 times the standard deviation of group 1 squared. Let me move this out of my way. And where's the standard deviation of group 1? It's all the way over there. I wish I had put it over here. Hang on a second. Let me copy this over here so it makes it a little easy for me. Of course. Okay, males. Yeah, it's the apostrophe. I didn't knock out the apostrophe. Okay, good. Equals females. Okay, so I'm over here now. So I'm gonna build up this equation from the different parts of it here. Okay, so first of all, in the on the top of the in the denominator here, I've got n minus 1, which is going to be equal to 8 times the standard deviation for males squared, which is going to be this number times itself. Okay, everybody okay with that? Okay, now I'm going to calculate n2 minus 1 times s2 squared. It's going to be equal to, let's see, it's going to be equal to 8 times standard deviation of females squared. That's, by the way, what is that called when we square the standard deviation? The variance, right. You get the standard deviation by square root of the variance. Okay, now let's calculate the bottom of this. N2 plus N1 plus N2 minus 2. So that's 9, and 9 is 18, minus 2 is 16. Okay, so here we go. Okay, now let's calculate this square root. Equals the square root of this number plus this number, right, divided by 16. Okay, the only thing is I have to put another parentheses in here. Okay, so that's going to do the top first and divide and then find the square root. And we got 2.37. That's our pooled standard deviation. Okay, so now let's calculate what our t-score is. What's our t-score going to be equal to? Our t-score is going to be equal to the difference between the two means, which is difference between, where are the means now? Where'd the means go? 10 minus 7.5 well, equals, parentheses, 10 minus 7.5 divided by, well, now it's going to get a little complicated again, isn't it? Okay, so I'm going to calculate the top first, then I'm going to calculate the bottom. Bottom's going to be equal to the pooled standard deviation, 2.37, right, times the square root of 1 over 9 plus 1 over 9. Okay, now they're not always going to be the same number, right? Depends on the sample sizes. Could conceivably be different. So let me make sure this is going to add these two together. Find the square root and then multiply it by the pooled standard deviation. So that's going to be equal to that. So the t-score is going to be equal to 2.44 divided by 1.11. It's going to be equal to 2.18. Okay, so now, can I reject my null hypothesis? Is my t-score big enough to reject my null hypothesis? What do we need to know now? What's the critical value of t? How big is our, let's go get our t-table back. Let's go find our t-table. Where is our t-table? It's here somewhere. I'll bring it back up again. So how many degrees of freedom am I working on now? I pool the two groups together. So what do I do when I pool the two groups together? Remember what it said there? What did it say there? Degrees of freedom is equal to 1, n1 plus n2, 9 and 9, 18, minus 2, 16 degrees of freedom, right? So what is the t-score I have to exceed for 16 degrees of freedom? Okay, that's going to be 2.12, right? And what was my t-score I calculated? I lost it. 2.18. Is it greater than my critical value of t? It is. So my t-score is an indication of what the probability is that I would get this result if the two groups had the same means. Okay, I would get this result less than 5% of the time, right? Because my t-score, my critical t-score is exactly 5% of the time. A bigger t-score means it's less likely. Right? So our t-score is greater than our critical value of t, so I can reject my null hypothesis. Okay? I see a lot of stunned faces out there. So now, all of you people have been complaining about SPSS all this time. We're going to try this again in SPSS. Right? As a matter of fact, I gave you a data set already that is exactly the same as this. Okay, 2-sample t-test .sav. Let's see if I get lucky if it'll open right from there. It takes a moment or two there. more than a moment or two. Let me see what's going on with the guys at home. Okay, how's it going in the peanut gallery there? Oh, some people are actually giving me some feedback here. Can you make me the presenter? Yes, I can. Why would I want to do that? Hey, Joshua, do you have something you want to try? Okay. Okay, so general network error, whatever that means. I hope that doesn't mean anything bad. Okay, so let's take a look. I think that's an SPSS. Oh, because it opened it twice. Let me close this one. Okay, so here we go. These are the same numbers, I believe, as we were just working with, right? So I have two groups, males and females, right? We can go back into the variable view here and we can fill in some information. First thing I want to do is it thinks it's a nominal data because the numbers are so small. I use like whole numbers and they're small. I'm going to make sure it understands that they're scalar data or numerical data, just in case it messes that up. Okay, so accident. Oh, I'm sorry, that was an accident. That request was an accident. Okay, I'm going to say analyze, and I'm going to go, where am I going to go? I'm comparing means here, right? That's really what I'm doing here. So I'm going to compare means. These are independent samples t-test. Oh, you want to know something? SPSS, my version of SPSS is really a little weird. And what it does is, I'm going to show you what it does. I'm going to go to descriptives, and I'm just for the hell of it, I'm going to find the means and standard deviations for males and females. Here we go. And we got the same, I believe, same male standard deviations that we got before for the example that I was, right? These look roughly like the same means and standard deviations. They're working on, the reason I did that because I have an output window here. For some reason, which makes no sense at all, when I click down on analyze with the output window open, I get a different group of options than I do with the data window open. And what I want to get, yours should show this all the time. I'm going to go to compare means. I'm going to go to independent samples t-test, right? One sample t-test would have been what we did earlier. But now I'm going to independent samples, two independent samples t-tests. Okay, I'm going to go in here. Okay, oops. Let's see, something went wrong here again. Analyze, compare means, independent samples t-tests. Okay, test variables males and females. Oh, you know what? Oh my goodness. The data is not formatted for this. Okay, this is going to get ugly now, but it's good that you saw this, right? SPSS, as far as SPSS is concerned, these are two different variables, and it really can't work with comparing the two of them, the means of the two of them. So what I'm going to do is I'm actually going to take these 9 values and I'm going to copy them down here. Okay, and then watch what I'm going to do here. I'm going to change this to a 1 and copy that all the way down. Okay, and then from 10 on, I'm going to call it 2. Okay, good. And now I'm going to go to the variable view. Now my two variables, my first variable, I'm going to call value, whatever that number happens to be. My second variable is going to be gender. Okay, so now gender is a nominal variable. Right? I'm going to make sure it knows that. I'm going to go into values and I'm going to tell it that a 1 represents males and a 2 represents females. Okay, and I'm going to go back here. See, so when the data was formatted in Excel, it was very convenient to have the males and females in 2 columns. In SPSS, it's much easier to work with the data formatted this way, where I have the variable gender in one column and I have the variable, the value, whatever that number represents in the other column. You guys see the difference here? So now when I go to analyze, compare means, again, let me go to the output window. When I go to analyze, compare means, independent samples t-tests, now I can tell it that I want to compare the averages of those values And I want to group those by gender. I want to find the means of males and females and compare the two of them. Now, unfortunately, for some reason, SPSS is not smart enough to realize that there's only ones and twos, right? So I'm going to click on define and tell it that group one is represented by ones and group two is represented by twos, and click continue. So now I can click on options also. So notice I have an opportunity here to put in a confidence interval. If I want an alpha error of 5%, right, type 1 or an alpha error of 5%, I want to only have a 5% chance of being wrong if I reject the null hypothesis. I leave this at 95%. If I want an alpha error of 1%, what should I change that to? What's that? No, you change it to 99%. It's the confidence interval, right? Okay, if I wanted a alpha error, if I was willing to accept a chance of an alpha error of 10%, what should I change that to? 90. Good. Okay, good. We got that. That's clear, right? Okay, so I'm going to say okay, and it's going to do that same t-test that we just calculated. Okay, in fact, it finished it already. Okay, let's take a look at it. What's the value for t? Well, hang on a second. It actually gave us two rows here, right? Look at this. Instead of it did the calculation for the mean and standard deviation again. But look, it gave us two rows where it calculated the t-score and some other stuff, right? Why did it give us two rows? It gave us two rows because it first calculated it assuming equal variances, and it then calculated assuming unequal variances. Okay, so now let's think about this for a second. Okay, which of these two rows should I use? Well, we calculated assuming equal variances, right? So we would just stick with the top row if we were correct. Okay, so I'm going to go across here. What's the t-value? 2.184. Isn't that what we got? Right, we got the same thing. Now, next to it's got degrees of freedom 16, the same thing we calculated. How about the significance, two-tailed significance? That's our p-value. That's the probability that we would get this result, even though the population means were the same. Another way of saying that is the probability that when we reject the null hypothesis, that we would be wrong because they really are the same means, right? So we want that probability to be less than 5%, so that's our p-value. Okay, we want that to be less than 5%. So if our t-score is bigger than our critical value of t, that's always going to be less than 5%. Is it less than 5%? It is. So it confirms we can reject the null hypothesis. So besides the fact that it was able to do this in an instant instead of having to go through all those calculations and do it more accurate, I mean, the most likely, right? Besides that, it also produces a p-value, which actually gives you some idea of what your likelihood of your making an error if you reject the null hypothesis. Where when we were using it by using the t-table, we only knew that we could reject the null hypothesis, right? It didn't really give us very specific information about how likely we would be to be making an error. So this gives us a bit more information. So now let's go back and think about this idea of equal variances assumed or not assumed. Okay, so see these four boxes over here where we're starting. Okay, let me kind of bring them up a little higher. SPSS doesn't allow me to zoom in like most of the other apps on here do. Okay, so you see those four boxes over there that are underneath the thing they label Levine's test for equality of the variances, right? That's actually a test to determine whether or not you should assume equal variances. So what's the null hypothesis, you think, for equal variances? Null hypothesis is that the two variances are equal. What's your alternative hypothesis? The two variables are not equal. So let's take a look at this. If you run this test, right, what's the probability that you would be wrong if you reject the null hypothesis? Well, is it less than 0.05? The significance less than 0.05? What does it say there? It says the probability, the significance for that test of equal variances is 0.245. Is that less than 0.05? No, it's not. So we fail to reject the null hypothesis. What was the null hypothesis? That the two variances were equal. And which row is that? That's the top row. If that number significance is less than 0.05, we go with the bottom row. If it's more than 0.05, we go with the top row, right? And if it's 0.05 exactly, right, you send an email to Professor Waldron and ask him what to do.
Call me at home.
Yeah, call him at